We have problem B3 from the 2025 Putnam today, where we have a set S of non-empty positive integers with the property that if n is in S, then every positive divisor of 2025 to the n minus 15 to the n is also in S. And we're asked, does S contain all of the positive integers? So I guess it'd be pretty cool if it did. And so I guess how we should start is what's the sort of worst case scenario to try to get that S actually does not contain all the positive integers, right? So we know that S is non-empty, so there's at least some integer x in S. So if we consider 2025 to the x minus 15 to the x, no matter what x is, we always have at least that 1 divides this, right? Because 1 divides everything. So that implies 1 is in S. So in fact, it makes sense to say that the worst case that we can start with is if S is just the set. If we start with just 1 in the set S, right? And then see what numbers we can get from there. Alright, well suppose we just have 1. Then we can really only analyze 2025 to the first power minus 15 to the first power, which is 2010. And so we have that 2 divides 2010 since it's even, so 2 is in S. We have 3 divides 2010 since the digits sum to a multiple of 3, so 3 is in S. 4 doesn't divide 2010, but we can at least say that 5 divides 2010 since it ends in 0, and since 2 and 3 divide 2010, then we also have 6 divides 2010 as well, right? So how can we try to get 4? We can look at 2025 squared, right? Just try the next number and see what factors we can get from there. And I guess we can, this is pretty big to evaluate. I don't want to square 2025. So we can just consider this entire expression mod 4. We're hoping to get that it's congruent to 0 mod 4. And so it's well known that any odd number squared will be congruent to 1 mod 4 because any odd number is either 1 or 3 mod 4, so squared that's 1 or 9, which is both congruent to 1 mod 4. So yeah, this is congruent to 1 minus 1, which is congruent to 0 mod 4. So we indeed have that 4 divides 2025 squared minus 15 squared. So we have that 4 is in S. We have 5 and 6, but what about 7? Yeah, we can't necessarily tell. You sort of just have to try, a bunch of these powers and see where you get. But I guess if you just try 3, I think you'll get that 7 divides this. I think 2025 is congruent to 2 mod 7, and 15 is congruent to 1 mod 7. So that's 8 minus 1 is congruent to 0 mod 7. Right, so that means 7 divides 2025 cubed minus 15 cubed. So 7 is also in S. And I guess you could keep going and sort of try out different numbers and see if they also are in S. But at this point, I think it's reasonable to assume that maybe S indeed does contain all of the positive integers. So our goal then our goal now is to sort of show for any n in S, is there a good choice, let's say M, is there a good choice for M, such that hopefully M, a function of N, such that N divides 2025 to the M minus 15 to the M. And as note that 15 divides 2025. So if we can try to find some pattern, we can write 2025 M minus 15 M is equal to, factor out the 15 to the M. This will be 135 to the M minus 1. I guess, which is 3 to the M times 5 to the M, 135 to the M minus 1. So if we want n to divide this expression, then I guess if we write n as sort of also in this form, right, 3 to the A times 5 to the B times some C, where I guess we don't have 3 and 5 both do not divide C, right? So these are the maximum powers of 3 and 5 that divide n. Then if we can show that if 3 to the A divides 3 to the M, 5 to the B divides 5 to the M, and then C divides 135 to the M minus 1, then we just immediately have that n divides our expression, right? And so looking at this, I guess in particular focusing on this part, if you've sort of taken a number theory course or have done number theory in the past, this should remind you of sort of Euler's-Tauschen function, or Euler's-Tauschen function and Euler's-Tauschen theorem, where I guess a quick refresher, Euler's-Tauschen function defined as phi of n is equal to the number of relatively prime numbers, number of relatively prime positive ints less than or equal to n. And so Euler's-Tauschen theorem gives us a nice relationship between n and certain powers, where if we have a and n to be relatively prime, then a to the phi of n is congruent to 1 mod n. And this is sort of a generalization of Fermat's little theorem, which is, in particular, it focuses on prime n. And so I guess how this relates to our problem is if we look at the C dividing 135 to the m minus 1, since we forced 3 and 5 to not divide c, we know that c I guess we know c is relatively prime to 135, because 135 is equal to 3 squared times, I guess 3 cubed times 5. Right, and because we enforced that 3 and 5 don't divide c, we have that c and 135 are relatively prime. So the idea is we can actually make m is equal to phi of n, right? We can choose m to be phi of n to try to make this case work, right? So for the case where c divides 135 to the m, or now we can write it as phi n minus 1. As starting with Fermat's or Euler's-Tauschen theorem, we have that 135 to the phi of c is congruent to 1 mod c. But the thing about Euler's-Tauschen function is that it's multiplicative. So what that means is we have that phi of n is equal to phi of how we wrote it before, 3 to the a times 5 to the b times c. And by multiplicative, I mean that this is equal to phi of 3 to the a times phi of 5 to the b times phi of c. So in particular, that means that 135 to the phi of c raised to the phi of 3a times phi of 5b is still congruent to 1 mod c. But this is exactly n, right? So we have that 135 to the n is congruent to 1 mod c. And so we indeed have that c divides 135 to the n minus 1. Now the last case, or the last two cases, I guess, is to show that 3 to the a divides 3 to the m, and 5 to the b divides 5 to the m. So for the 3 case, this is equivalent to showing that a is less than or equal to, or let me make this 5. This is equivalent to showing that a is less than 5n, and there's actually an explicit formula to find 5n. But just using it for now, I won't derive it. Here, the 5n, again, writing it in the way we had up here, is equal to phi of 3 to the a times phi of 5 to the b times phi of c. This is surely less than or equal to just phi of 3 to the a, which is equal to 3 to the a plus 1 minus 1 all over 3 minus a. And this is 3 to the a plus 1 minus 1 over 2. And we indeed have that this is always greater than or equal to a. I guess for all a in the positive a. I guess you can sort of prove that more vigorously with induction, but you can sort of reason that this grows exponentially, this grows linearly, and we have that for the first couple of a. Let's say a is equal to 1, 2, 3, and 4. We have the inequality holds. So surely for bigger a, the inequality should still hold. And so similarly for the, or I guess we have having that a, this implies that the 5n is less than or equal to a. So we have that 3 to the a divides 3 to the 5n. And similarly for 5 to the b dividing 5 to the 5n, we have that again 5n is equal to 3a times 5b, or sorry, we want to again show that b is less than or equal to 5n. So writing 5n in this way, and then again focusing on just the 5 to the b, which this is equal to 5 to the b plus 1 minus 1 over 5 minus 1 is equal to 5 to the b plus 1 minus 1 over 4. And we also have that this is greater than or equal to b for all b in the positives. And for similar reasoning, right? This grows linearly, this grows exponentially, and for the first few b in the positive integers, the inequality holds, so surely it holds for all higher b. And again, you can prove that more vigorously with some sort of induction. So now, given all three of these cases, based on what we said before, we have that this is true. Our if statement, or I forget what it's called, but our condition is true. So we indeed have that n divides 2025 to the phi of n minus 15 to the phi of n. And so how does that help us with our problem, right? With showing that s is all of the positive integers? Well, we can note that phi of n is less than or equal to n, right? Because up here is defined as the number of relatively prime positive integers less than or equal to n. So there's at most n of those. So we have that phi of n is less than n. And so this motivates just using strong induction to finish out the proof. And so what this means is we have our base case. We have 1 as an s. Alright. And then for our inductive step, I guess trivially, for our inductive step, or inductive hypothesis, for fixed n, assume 1, 2, all the way to n are also an s. Then our inductive step is just, or make this easier, for fixed n minus 1 is for fixed n minus 1 greater than or equal to 1, assume that 1 all the way to n minus 1 are all in s. Then for we want to show that n is also an S. Then for n, we have that 5n is less than or equal to n. And I guess this is actually strict, because 5n again counts the number of relatively prime positive integers less than or equal to n, but n cannot be relatively prime to n. So we really only consider 1 through n minus 1, and there are n minus 1 integers. So this is actually strict. We have 5n is less than n, so that implies 5n is in S by our inductive hypothesis. And so all divisors, or I guess then when we showed that n divides 2025, the 5n minus 15 to the 5n, n dividing that means, or I guess just implies again, n is also an S. And so by induction, we just have S is equal to the entire, all of the positive real numbers. And that completes the proof.